Okay, good afternoon, everyone. My name is Elena Pourmal, and I learned that we do not have any questions so far submitted to the form. And before I start on the topic of chunking and compression, I would just like to ask if people who joined have any questions that were not submitted. If not, then I will proceed with the presentation. No? Okay. So today I chose the theme of chunking and compression, and I see something in the chat. Oh, no questions. Okay. Chunking and compression is one of the topics that our users mostly ask about. And the reason is because it's create a lot of performance issues that, frankly speaking, can be very easily resolved. So this presentation is about just case study that probably affected, 80% of the cases, and how you can tune performance based on different chunking and compression parameters. Let's see why my mouse is not. Okay, so the goal of this presentation is, as I said, to understand how chunking and compression parameters work and how you can efficiently store and retrieve data from HDF5 files. And usually like people write their data and think someone will be easily read it. And sometimes, and pretty often, it's not the case. That's why both data providers and data consumers have to be aware when they use chunking and compression feature, how it affects performance on both sides, on writing and on reading. This is a real use case that our help desk received. We were pointed to a file that was produced by NO when NPP program started. It's just not Pearl satellites that are on orbit, stationary orbit, and they gather a lot of data during runs and put data in HDF5 files. HDF5 file usually has several, like 10, 15 data sets, and data sets are pretty big. This is an example of imaginary data, which is 46 megabytes. It's stored as chunk data set. And you see chunking parameters here. So those are dimensions, and chunking is done along fastest changing dimension. And there are 15 chunks for this particular data set. And the applications were reading that file, that data set just once, but a read pattern was by scan line, by the last changing, fastest changing dimension. So it was contiguous one by one by 717 element selections. So 717 elements were read because there will be 16,200 scan lines, 1,600 times. And the time to read the whole data set with compression and without compression is many orders of magnitude. So when that data set was compressed with gzip level, which gave pretty good compression, it took 345 seconds versus when there was no compression, it was just 1/10 of the second. So when people come, what can I do? Performance really depends on many factors, especially on access patterns, chunk sizes, and chunk cache, and that will affect your memory usage, and of course compression algorithms and chunk layout in general, how data is chunked affects your performance. So solutions that we'll talk here will be oriented just to this use case when we're reading entire data set by a contiguous selection along the fastest changing dimension. But I really hope that a troubleshooting approach that I will show you here will apply to many more cases, and you will understand how internals of HDF5 works, so you can tune your application properly. So the first thing, I just will give you the results, and then we go into details of those three tuning techniques. The first recommendation will be, if you can, on if you can access to your application, modify it and increase chunk cache size. And in this particular case, we increase chunk cache size from 1 megabyte, which is the default, to 3 megabytes to contain the whole chunk. And performance was drastically improved, order of magnitude. So you see from 35 seconds to 1/3 of the second. Another way to do it is just change access patterns. So instead of reading by one row, read the whole chunk that will contain many scan lines. Once again, you will get about the same performance, and we will see why. And the third tuning technique, it is only that data providers can do. It's really think about chunk size and write original files with a smaller chunk size that they fit to cache. And we just create a chunk size by reducing it, so it will be 1 megabyte. So instead of 4 being first dimension, we used 1. It was less than 1 megabyte, and you see that the performance was the same, about the same performance when we use compression. And it's kind of comparable, more comparable when no compression was used, which was very desirable for our application. So let's quickly do some chunking overview. If you want to find information, I highly recommend you to go to portal, to HDF5 documentation, and under HDF5 application developers guide, there will be general topics that will cover chunking, compression, and there will be some technical notes how to improve compression and how to troubleshoot compression. So if you want to go, you will find a lot of information. So before we go and jump into what is all it's about, I would like to remind you, what is HDF5 dataset? You know that dataset has it is data array of elements of particular data set, and there is to make this data array self-descriptive in HDF5 library, some metadata, HDF5 metadata is stored about this data array. It is stored in so-called dataset header. It is a small object that is stored as separate entity in HDF5 file, and it contains information about dimensionality, about data type. It also contains user-defined metadata as attributes, and it has information about storage, how dataset is stored. Is it chunk? Is it compressed? It's contiguous storage, and so on. So when dataset is contiguous, this is how it will look like in the file and application memory. In application memory, there is a buffer. It can be smaller buffer, or it can be the whole array. There is in metadata cache that is an application memory. There is a dataset header that is written when dataset is created. Dataset header with all information is created. It is data array is written to the file, then data set header is evicted from metadata cache, and data set header has a pointer to where data is located. So very simple, not much overhead in terms of special metadata that has to be stored along with the data array. So the story is very different when we go to chunk storage. So this is the difference between contiguous storage and chunk storage. Chunk is contiguous is stored as one contiguous block. I'm sorry, my mouse is jumping along the fastest changing dimension, so it will be contiguous block on the disk. When data storage is chunked, I don't know what's going on. Then data array is divided in equal size chunks, and each chunk is stored as contiguous block in the file. I will try. Chunking is required for several HDF5 features. For example, when you want to add data along different dimensions, and as you know, in HDF5, you may add data along any dimension, not only fastest changing dimension like in NetCDO4. And compression, application of compression and other filters, for example, like checksum or bit shuffling, is required. It applied only to data sets, data arrays that use chunk storage. And you can see it's very beneficial for, especially in this case, we applied only not gzip compression, but we also shuffle before we applied gzip, and we got much better compression ratio. So this is a desirable feature to use. Of course, chunking improves performance, because in this case, for example, on the left, you see we want to read green rectangle, and we need to really read contiguous part of the data set, and then HDF5 library scatters this data to user buffer, while in chunk storage, only 2 chunks that contains this hyper slab will be read into the library. So much less IO may be required when you're doing especially partial IO. This is kind of illustrated what I was saying. Chunking strategy is extremely important when you create your data. In our case, in this particular use case, because of the instrument, data was written and chunk was chosen by the buffer that was coming from the instrument. And for that particular data set, they call it granule, because this is what instrument on satellite was picking up. And that what determined the chunk size being more than 1 megabyte. And you see, it's clear that it was very preferable for the write, because it was written by chunk, which was 4 megabyte, pretty good size of IO operation. But for reading, for example, if you want to read one row, one column, you will need to read all data. Because data contains in each chunk, each piece of the column has to be extracted from the chunk. And if data is compressed, then you have to really uncompress all data just to get one column. It's really, you have to think how data will be used before you choose how your chunk strategy. It may be favorable for the write, but not be extremely unfavorable for the read, obviously. Using chunk storage also creates some overhead in terms of different IO operations. First of all, in the file, now dataset header will point first to chunk index, and chunk index will point to different chunks that may be scattered in the file. They may not be contiguous chunk by chunk. They may not be written one after another. It really depends what application is doing. So for example, if you open many data sets at once and you start writing to those data sets chunk by chunk into each data set, chunks will be allocated from different set one after another. But when your user open data set, they will need to jump through the file to find the application, jump through the file to pull out those chunks. How we mitigate this? We mitigate with chunking cache, etc. But be aware how you create chunk, how you use chunk storage, and when you write multiple data sets, because chunks are written as a whole in the file, and a library does know what it cannot allocate, for example, immediately all chunks if you do not instruct it, and chunks may be scattered in the file for one data set. Also, what is happening when you apply compression? In application memory, you have, say, chunk data set that's just your buffer, which is logically divided, and you're doing some IO. And in this picture, we're doing just IO on the chunk. So if chunk fits into the cache and you issue any write operation, chunk is placed in the chunk cache, and data type conversion is going before it placed in the chunk cache. When chunk is evicted from the cache, then all compression is applied and it goes to the file. So chunk stayed in memory space, not in the kind of user form, but already conversion is applied. So if you do not use type conversion, you may save some here without avoiding conversion when doing IO. So remember that you cannot change chunk size, right? This is a creation property. It is set up, and when you write, there is no way to decide, oh, I need to use bigger chunk. The only way is to finish writing and then use H5 repack to change layout. And how you do it? So there is special API. I believe it will be on the next slide. But how you choose the right chunk size? And unfortunately, there is no good algorithm. You really have to experiment, because if chunks are too small, you will end up with a file that has many chunks, which means a lot of extra metadata. There will be extra time to do lookup for each chunk when you do I/O, and more I/O, since I/O is done on each chunk, and it's done independently on each chunk. And independently, I'm talking here in a serial case. So we will read chunk at a time. And while larger chunks results in fewer chunk lookups, smaller file sizes, and fewer I/O operations. So you really have to balance what is your goal, what you're trying to achieve. If chunk are too large, then entire chunk has to be read and uncompressed before performing any operations. So you saw that slide with the pipeline. So when you read, we go through that pipeline, the whole chunk is uncompressed, placed in cache or not placed in cache. We'll see it in a minute. And it's really great performance penalty when reading small subsets, and especially when you're reading small subsets all over again and again. Entire chunk has to be in memory, and it may cause operating system to page memory to disk, slowing down the entire system. And especially may happen when you open a lot of chunk data sets. Each of them has the default chunk cache that is allocated immediately, and application memory will grow tremendously. So be careful when you're opening. Now let's go to case study that will go show why those three parameters that we talk about, changing access pattern, changing cache size, chunk cache size, and chunk size in general help the performance. So let's first look at chunk cache size. Just a little quick overview of what it is. First of all, this is the only raw data cache in HDF5, unless you use page buffering, which was introduced, I believe, in 110 series of releases. I mentioned that chunk cache is per data set, and really it improves performance only when the same chunk is read or written multiple times. So if you read or write by chunk, your access pattern coincide with the, each chunk, you may disable chunk cache, and this will help to reduce memory consumption for application. Default size of the cache is 1 megabyte. And imagine you have like 100, which is really cases we see, 100 data sets are open simultaneously to read from here and there. So we're immediately using 32 megabytes, and it may grow. As I said, chunk cache may be disabled. So what happened when we're reading, for example, on the left, chunks are stored in the file, and we're reading by row. So the first three chunk cache, when we issue the read request as a row, it is stored in 3 different chunks, and in application memory, this is a contiguous blue buffer. But library tries to bring all data that is requested into chunk cache. So in this good case, we put the chunk cache is big enough, we put all 3 chunks that contain the first row, and library reads from each chunk and scatters it into the application buffer. And since all chunks are in the cache, second and third read goes fast, because there is no need to go to to the disk, and also there is no need to uncompress data because uncompressed chunks are stored in the chunk cache. So caches really can help you when things are good, but sometimes you do not know they are good or not. So the first thing that you think when you see bad performance, look at your chunk size and think for access pattern. Does that access IO request, will this IO request fit into chunk cache? Because what will happen when chunk is cannot fit into cache because it's too small, especially when it's compressed, it is read, uncompressed, selected data converted to the memory data type as you saw in this data diagram and copied to application buffer. And what happened next? Chunk is discarded because it doesn't fit into cache. So this is a picture that exactly what our application dealt with. Granule, the chunk was too big. It was almost 3 megabytes versus 1 megabyte. We read from the disk, we uncompressed, we read the first row, and then instead of reading a next row, which will be our application next request, we were discarding chunk, and this operation was going on and on and on, resulting in 16,200 reads and decode operations. Instead, when we bring everything chunk fits in the cache, we'll have only 15 reads because all we need to read by reading by row, we only need to read our initial 15 chunks and then read rows from the memory that is application. So how you change the chunk cache? There are two APIs, and set chunk cache sets raw data chunk cache parameters for a data set, which is really convenient because you may still different data sets have different chunk sizes, use different chunk sizes, and you may tune for each data set. Your application may tune and find, okay, I'm reading the file with this type of a chunk size. I will at least set chunk cache so it fits. H5P set cache API sets for all data sets of the file. It's easy because you open the file, use access property before you open the file and set cache. But then for some data sets that have bigger chunks that will not fit, you may encounter this situation. And there are other parameters that for these APIs that control chunk cache. First its size we talk about, and then it uses very simple hash algorithm. There is number of slots in that hash table, which is 521, and there is preemption policy when chunks are evicted or when cache is full. So you can play with those parameters to improve performance. So this is exactly the picture after when we increase cache size and everything is in the cache, and we read all rows from each chunk without going to the disk. So sometimes it's easy to just, as we saw, just to change access pattern. We just read the whole chunk, right? And in this case, by the way, when chunks are compressed, the whole chunk is read uncompressed. It immediately copied to the user buffer, and chunk cache essentially is ignored in this particular case. So it is also then reasonable when you know that your access pattern will be by chunk. You may just discard a chunk cache tool and disable it, set size to 0. You will disable chunk cache saving application memory that HDF5 library uses in your memory space to work with chunks. This is picture illustrates what happens with access patterns. So we have chunk cache and chunk that doesn't fit, but it really uncompressed and immediately read into application buffer and then evicted. So there is no reason even to use chunk cache in this case. For application for data producers, you really have to think about what is the best strategy? Because you should understand that some people use applications where they cannot change any parameters. They have to work with the default cache size and with the default access pattern that application uses. So then recommendation is really try to use smaller chunks, try to use chunks that are at least several kilobytes. So several of them can fit into 1 megabyte default chunk cache. Then your users of your data will not need to modify the applications. And this is illustration, it just fits, and access patterns will be, even you read by row or even by column, there is still much less I/O is going on, because I/O will be done on the whole chunk, all data is in that chunk, and application can pull necessary data from there. So in summary, when compression is enabled, library always must read entire chunk for each H5D read, unless the chunk is already in cache. So for example, you create big hyperslab, it will read several chunks, put them in the cache, as many as it can fit, or it will read one chunk, but it reads I/O is done on one chunk. When compression is disabled, library behavior really depends on the cache size relative to chunk size. If chunk fits in cache, great. First of all, you'll have one big I/O, and then I/O goes from, data is not compressed, it's in the chunk uncompressed. It's easy to read, no decoding is going on, and data is copied. But if chunk doesn't fit in cache, then library bypasses cache and it reads, it tries to optimize to read contiguous blocks from the file, because in the file, in one chunk, data is stored contiguously. It will result in more read operations, but still, when chunk is not compressed, its performance is much better when it doesn't fit in the cache. So on the right, it's very similar. It's kind of opposite. But remember that if chunk doesn't fit in cache and compression is enabled, and not whole chunk is written at once, then what happens, since all writes to the dataset must be immediately written to disk because it doesn't fit into cache. With compression, entire chunk, you just modify, say, one piece of the chunk. But with compression, the entire chunk must be written, or if it exists, it must be read, rewritten, and compressed again and written again. So there will be a lot of decompression and encoding and decoding is going on. Since modification of the chunk compression will may change its size when it's compressed, HDF5 library will allocate new space to store that chunk. And it may result in larger file because chunk will be always, when it's done, written to new space, and space may not be reused. So when you do this with the chunks, overwriting chunks all over again, you will result in the pretty big files, and it may happen very, very quickly. So thank you, and I hope we have a few minutes for questions. I cannot hear. I don't know.
We don't have any questions yet.
Let's see.
Robert, yeah, Robert was talking.
Oh, yes.
Yeah.
No, I just had one question. That last point on the previous slide about the increasing file size.
Right.
Go over that again. What happens to the extra chunks that are overwritten?
Okay, so imagine we first we wrote a chunk, and forget about chunk size right now, right?
Okay.
Chunk cache size. So a chunk is written, and now I want to modify piece of the chunk. So the library reads chunk back because it's not in memory, it's not in cache, and uncompressed element is modified, and it changes the size of compressed chunk, right? Because compression may work differently. It can be smaller, then it can be written to the same space where it was allocated. But if it becomes bigger, library has to allocate another space to write it to the file.
I see. Okay.
And you may say to library, there is a free space managing in the file. Once again, in 110 release, you can tell library to remember those holes and reuse them when appropriate. At runtime, when your application is running, library will try to reuse that space as much as it can. But if you do not enable this feature, that place is essentially lost. When you open the file, library will not know about those spots that can be reused. So tracing of free space should be enabled. There are special APIs.
I see. So they can be garbage collected, but you have to turn on.
Yes.
I see. Okay. All right.
Yes.
Thank you very much. Got that.
Yes. So any other questions not related to this talk?
No.
Okay, thank you. Marta, do you have any question? Oh, Marta. Okay, so then goodbye.
Thanks, everyone.
Bye-bye.